Good morning, ladies and gentlemen, and thank you very much for joining us today for what promises to be a highly informative webinar looking at power distribution technologies for reliability and resiliency, brought to you by G&W Electric and hosted by Enlit Asia. My name is Simon Hoare. I'm the Portfolio Director for Energy with Enlit Asia, and I'll be acting as your host and moderator for the discussion today. As a brief introduction, G&W Electric is a US-based company with an over 100-year history of engineering game-changing innovations and working closely with customers to design unequaled, innovative power grid solutions that use its industry-leading products. This webinar comes at a time when across ASEAN, we are currently experiencing a period of significant flux, with the energy transition driving changes to a system that's remained largely untouched for over a century, forcing utilities and grid operators to consider the impact of high variable RE and the prospect of an increasingly digitalized and decentralized power network. This is combined with the ever-increasing instances of extreme weather occurrences in the region and the need to continue to deliver power to the nearly 700 million people across ASEAN. These factors are compounding the ever-increasing need for a reliable and resilient grid that can face the challenges the future poses head-on. I'm delighted today to be joined by three subject matter experts from G&W who will share with you insights into how their solutions have supported distribution operators worldwide and how these can be tailored to the unique challenges and environment in which ASEAN utilities are and will continue to operate in. The session today will be featured around a presentation from G&W, interspersed with questions. Please do not hesitate to ask any questions that you may have. Simply type them in the chat box and I'll share them with the panel. We will, of course, endeavor to get through them all, but apologies in advance if we're unable to do so. So without further ado, I'd like you to hand over to today's speakers. We have John Gunaris, Ron Pate, and Carl Stromberg. As they are speaking, please do not, again, hesitate to ask any questions you may have. Simply type it in the chat box, and we will do our best to come around to them. John.
Okay, thanks, Simon. Appreciate the introduction. Well, good morning, everyone. Thank you for the opportunity of being able to speak to you this morning. I'm joined by my colleagues, Ron and Kyle. I want to thank the Enlit Asia team for giving us the opportunity to be able to speak to you here. We have a lot of information to share with you and a very interesting topic to talk about. We're here to talk about technologies to help your utilities improve reliability and resiliency. And we may sprinkle a little bit in there about transmission technologies as well. So a little bit more about today's speakers. My name is John Gunaris. I'm G&W Electric's Vice President of Global Marketing. I've been with G&W for a little over 20 years. I've got 22 years worth of experience in the industry. I've got experience in sales, marketing, product management, a number of different disciplines. I'm also joined by my colleague, Ron Pate, who's G&W Electric's Global Product Line Manager for Overhead Technologies. These are technologies like reclosers and sectionalizers and so forth. Ron comes to us with 34 years of industry experience. He has a background in sales and marketing, product management, as well as some engineering. He also has the distinction to participate and lead some IEEE groups as well, spreading his knowledge throughout the industry. And lastly, I have Kyle Stromberg, who's G&W Electric's Global Product Line Manager for Underground Technologies. So these are some of the distribution switches that G&W Electric offers to the market. Kyle's had a number of roles in applications and leadership positions in marketing and product management. Kyle brings 13 years worth of experience in the industry to today's discussion. And before I get into just kind of set the table for our discussion today, I wanted to find an opportunity to talk a little bit about who G&W Electric is. Maybe many of you know who G&W is, has worked with G&W Electric in the past, but maybe a little bit more background on who we are might be helpful. We're a power grid equipment manufacturer. We're located in Bolingbrook, Illinois, USA. Bolingbrook is near Chicago. So if you're familiar with where Chicago is, that's just about where Bolingbrook is. The company is privately held since 1905. So we've been operating in business pretty much since the beginning of the distribution industry in the United States. We are very proudly engineered to order. We like listening to our customers, understanding what their problems and then design a solution that meets exactly the requirements of that application. We back it up with outstanding customer service, outstanding innovative technology, and we build that technology to last decades and decades. G&W Electric is a global company. We have 7 factories over 5 different countries. We have 2 factories actually in the Bolingbrook, Illinois campus, but we also have a factory in Brampton, Ontario, Canada, which is near Toronto. We have a factory in San Luis Potosí, Mexico. We have 2 factories in northern Italy, one in Ferrara and the second near Venice. And we also have a factory in Shanghai, China. We're known for a number of different products, a number of recloser product lines, the Viper and the Taros. The Viper is available in both medium voltage, your traditional 15 to 38 kV class type equipment. It's also available in a unique industry-leading 72 kV version. The Taros is a medium voltage only type product. We also offer a number of secondary distribution switches in both SF6 insulation as well as solid electric insulation known as the Trident. We manufacture a number of cable accessory products, both joints and terminations, medium voltage as well as high voltage, sold as our Python product line. We carry a very unique high-powered current limiting system protection device known as the clip. This is a medium voltage device, extremely high continuous current, thousands of amps of continuous current, very high fault interrupting rating, and a unique product that can that acts like a current limiting fuse and can quickly remove very high fault currents from your system, thereby protecting your overall distribution. We participate in the smart grid by utilizing our power grid automation team, the laser team, as well as combining our high accuracy sensing technology into our products. One fun fact about G&W is we just recently energized our microgrid for our headquarters. Our microgrid is about 2 megawatts in size, and it includes solar generation. It also includes a backup diesel generator. It has a very unique vanadium redox flow battery system, one of the few in North America. It's a 2 megawatt size system for 8 megawatt hours of backup time. We also include a megawatt flywheel for instantaneous backup power for our most critical manufacturing operations. If you ever find yourself in the Chicagoland area with some free time, by all means, please give one of us a contact. We would love to give you a personalized tour of our microgrid. We're very proud of it and like to show it off. So I wanted to spend a couple of minutes here just setting the table for the discussion that we're about to have by talking a little bit about the challenges that many of you are facing today and what G&W Electric thinks you will be facing for tomorrow. And the way I like to have this conversation, all of us have whatever our starting point is for this journey, and all of us are going to see some significant changes, a changing grid over time. And we like to use a model that we call the 3Ds to kind of define what the grid, the next generation grid will be, or what we call grid 2.0. And this slide kind of summarizes what those 3Ds are. We'd like to start with decarbonation. They're at the top. Inclusion of renewables and reducing carbon footprint of the equipment that operates on the grid. Talk a little bit about digitalization, which is smarting the grid, adding things like information. And then we'll talk about decentralization as well, which includes not only renewables, but efforts that are needed to harden the grid. And I'll share a slide on each one of these points to explain how G&W sees one of these trends impacting this grid 2.0. And then that will segue nicely into let's start with decarbonization and the impacts of climate change. I think all of us here are very well aware of what these impacts are. We've been seeing the impacts of climate change increase the number of both low impact events as well as high impact events. So both reliability and resiliency type events have been impacted by climate change. Things like typhoon and wildfires, things that used to be 100-year storms are now unfortunately much more. All of this is driving a trend to decarbonize the electric power grid and include more equipment that has a lower carbon footprint. And basically what all of this means is that we're seeing the addition of a lot more renewables grid, and that's having massive changes. Obviously, it's a much more distributed grid now. We're moving away from the centralized generation model, and this is opening up the possibility of two-way power flow, which is having huge impacts on control and protection. One of the impacts that we are seeing globally is not only is there the possibility of more generation being available on the grid, but we're also expecting an increase in the amount of electric power that we are expected to consume. And all of that is driving much higher fault currents, what could be much higher fault currents in the future. And underlying a lot of these renewables is the fact that many of them are inverter based, and that creates the possibilities of more harmonics being introduced to the system. And we have new very impactful power quality issues that we feel will become the norm in the future. So all of these things combine to have many impacts, many of them negative, to the reliability and resiliency of the distribution grid. And layered on top of all of this is the potential for new environmental regulations and requirements. Some of you may already be feeling this. Some of you may not have yet. The trends are somewhat unequal. But the global trend is definitely to reduce the reliance on more traditional type solutions, such as after-fixed installation. That type of technology may be restricted or may not be available for you to use in the future as we move through this change. The next one I want to talk about is digitalization, adding more intelligence to the grid, more sensing and more control. So we talked about decarbonization, adding more renewables, a more distributed grid, and really what that's going to drive for us is the need for more real-time monitoring of what's going on. You're going to need more protection, more switching, more control. The possibility for more automation opens up in such an environment. And one of the challenges that all utilities globally will have to face is we don't get to start with a brand new grid when we move into this new era. We have to retrofit these new technologies onto the existing infrastructure. And this will be a massive challenge for many utilities to navigate. One of the things that we expect from digitalization is the improvement of grid efficiencies. These technologies offer the possibility of being very targeted and very efficient with how power is distributed, but it also offers the possibility through new regulatory structures and business models to change the way consumers of electric power interact. Can be quite exciting, but they will also be challenging and maybe even confusing as we navigate through them in the short term. Many of these capabilities rely on improvements that will be needed in software as well as communications security. We talked before about the need for more switching and more control and more protection and more sensing. All of that is going to drive up the need for more data analytics, higher speed communications, more secure communications to process all this data. And you won't be able to hire enough people or have enough money to be able to analyze all the data that's coming at you. We will need to be much more intelligent about how this data is analyzed and what trends are lurking there that is important for utility to be able to operate their grid more effectively. And the last slide I wanted to go over before I turn it over to our question and answer session is about decentralization. So we talked a lot about renewables, how that's driving a decentralized grid and the need for hardening the grid. All of us are operating in environments where our infrastructure is aging. G&W hears from many customers all over the world how they're operating equipment that's 10, 15, 20 plus years old in age. And this is driving not only a lot of concerns on reliability due to the age of the equipment, but the environment in which that equipment is operating, such as more severe environment, higher fault current, more harmonics. All of these combine to create a much more difficult environment for existing assets to operate. And it has the effect of not only impacting reliability, but it also has the impact of increasing our maintenance costs and just making it much more difficult to keep the existing operating and just keeping the lights on. All of this drives the need to select equipment and technologies that are hardened to be able to survive what we expect to be a future that includes more storms, more violent weather, and a much more dynamic electrical environment on the grid. And to drive home a previous point that I made, all of this needs to be done with a very diverse set of equipment on the grid. Interoperability is going to be critical to allow all these different components to work together seamlessly. And utilities will be challenged to find manufacturers, work with suppliers that allow their equipment to be operated with other devices seamlessly, that do not use proprietary technology or communication protocols, that make this interoperability as easily as possible. And one trend I definitely wanted to talk about related to decentralization is microgrids. More and more of your customers who demand premium are going to be looking for solutions outside of the traditional power grid. It's one of the reasons why I mentioned why G&W Electric has created and built its own microgrid for our headquarters. It's because we needed more reliability than what our local utility could provide. And so we built a microgrid to provide that premium power that we need, that our manufacturing operations never suffer a power loss due to it. So with that, I wanted to open us up to a question and answer session. Simon, to you.
John, thanks very much for that. Lots to sink our teeth into. I noticed that on the decarbonisation piece, you touched on the need for hardening. Carol, can I ask you to outline some of the strategies for grid hardening?
Yeah, absolutely. I'd be happy to talk about that. A good place to start is something near and dear to my portfolio, and that's a trend that we've been seeing in North America and a few other regions, which is an increased effort to actually underground distribution cable systems. Distribution cables can be carried either overhead or underground, and traditionally underground circuits have been viewed as a fairly high cost option for grid hardening. However, with all the things that John mentioned, changing in the industry, increased extreme weather events, a focus on more resiliency in the grid, the economics are starting to shift, and we're seeing more and more customers drive larger undergrounding projects and efforts. The main benefit of undergrounding your cables, of course, is it shields your circuits from severe weather events, high winds, ice storms. It also provides protection from vegetation growth, animals, and other events that can cause reliability issues on overhead circuits that are more exposed to those elements. So really tangible improvements to not just your reliability indices, SAIDI, SAIFI, but also some really nice plays to helping the overall resiliency. At G&W, as John mentioned, in our portfolio, we have a very robust set of underground switchgear that is capable of supporting and connecting to these types of circuits for sectionalization applications, protection applications. Like John mentioned, we have SF6 switchgear, which is very mature. It's been in the industry for over 50 years. We have that available at a very diverse set of ratings. Over time, we've seen a push from the industry to move away from technologies like SF6 that have a negative environmental impact. So for several decades, we've been building out a solid dielectric insulated portfolio for underground connected applications. And one of the things that we do with this portfolio, as John kind of hammered in his intro, is we emphasize customization capabilities. In North America, there's a couple of diverse locations where the cables may be buried underground, but where there's real estate to connect the switchgear devices, to connect to those cables, is greatly varied depending on geography, whether it's an urban or rural area. And we have switches that go above ground. We have switches that actually go below ground. And that paired with each utility's unique set of space requirements, operational requirements, has driven us to create a portfolio that's capable of a lot of customization to dial those pieces of equipment into our utility partners' needs. If we're talking about hardening of the actual equipment, which is very important, some of the things I can recommend utilities to do when specifying equipment. One is look at specifying equipment rated for outdoor conditions. Whether you're installing equipment outdoors or even if you're installing indoors with risk of extreme weather impacting that environment, outdoor rated equipment can really provide some major advantages. For example, we're seeing more and more extreme weather conditions from a temperature perspective. Extreme colds, extreme hots, swings back and forth more violently. So specifying equipment with a large temperature range and the ability to see variation and a test protocol that tests for that in the design and validation of that equipment is very important. Of course, durability of that equipment is critical. So having equipment that's manufactured with materials to withstand grid conditions, but also live a very long life. Specifying equipment capable of withstanding decades worth of service is a really good move to not have to be consistently changing out equipment or dealing with things that age quickly or are impacted by the environment in a short number of years. Some other considerations: looking for equipment that is capable of withstanding some kind of extreme scenarios. So one being, I mentioned in North America, we put a lot of distribution equipment below ground. That means that from time to time, that equipment does come into contact with water, and sometimes quite a bit of water during events like hurricanes, floods from extreme rains. This could be something that happens from a typhoon. Equipment that's capable of withstanding that temporary influx of water can do wonders for recovering from that storm. So all those things I just listed are actually some of the core principles about what we've designed into our underground portfolios, whether it's our SF6 or our solid dielectric Trident line. All those things I just discussed are things we've designed into our product. We've even done in some select applications, even more extreme testing for specific environments. For example, seismic testing for earthquake-prone areas in applications with critical loads that cannot lose power at any point in time. I think it's important to consider maintenance. Everything that we manufacture in our equipment is either no maintenance or extremely low maintenance. We've seen a huge shift in trend that with the complexity of the grid, our utility partners are spending more time diagnosing those problems, managing an old and more aging fleet, and they need their assets to be low maintenance and not out in the field, tending to them to keep their feeders and laterals providing power. If we step away from the apparatus a little bit and we think about the system, some of the trends we've seen that support hardening are increased automation. So moving away from maybe a traditional approach of manually operated switchgear to adding sensors, voltage, current, position indication, pairing that up with things like motor actuators or magnetic actuators that are capable of operating that equipment without a human being at the site. Those can unlock some pretty powerful applications for hardening of the grid, like automatic source transfer, FLISR, fault location, isolation, and service restoration, or like John mentioned, even a full microgrid that's capable of generating, storing, and islanding itself from the grid. So those are a couple of areas that we've certainly helped a number of utilities harden their grid.
Thanks. Ron, I suppose this is something that we should perhaps have started with. Maybe you could open up with a bit of an introduction or a bit of an overview of what the difference is between reliability and resiliency, and then perhaps touch on some of the solutions that are available to improve either of or each of those.
Sure, be glad to talk about that. And this is a topic that is, I would say, changing a bit in terms of focus. Historically, for decades, we've talked a lot in the utility industry about this concept of reliability. And as John had mentioned earlier, reliability, and I think Kyle mentioned as well, is about everyday steady state, keeping the lights on when you have events that occur that are relatively low impact overall, but have a pretty large frequency. You have tree limbs hitting, you have a squirrel that hits on a piece of apparatus, or a bird that shorts out. Maybe an accident or something occurs that shorts a power line out. So these things happen on a regular basis, and there's technologies and strategies that help us to deal with that we've been working on for many years. Some of the things, for example, you can do to improve reliability is putting in place more switching apparatus, such as reclosers, sectionalizers, load break switches, and then carefully planning and coordinating those so that you can get the maximum benefit from the least cost possible to get maximum benefit. And then you can start fairly simply putting out some of the apparatus, and then later you can follow with more sophisticated automation, et cetera. Another thing that's very common for dealing with reliability challenges is preventive maintenance on equipment, making sure that you also not only protect and maintain the equipment, but you also focus on the environment. So how you plan your distribution lines, how you make sure you trim trees and get other types of threats that could create these type of events, those are all very important aspects. And that's something that we've been very active in for nearly a century now in terms of enhancing the grid to provide more reliable service, such as different types of reclosers, different types of sectionalizer switches, that can be custom tailored to fit the exact application need. Sometimes buying one type of equipment and putting it across the entire grid might not be the best strategy. It might be to work where you have flexible options. For example, we have reclosers, we have sectionalizers, and we have different form factors for some of these as well, and kind of tailoring it so you can fit it exactly to the distribution strategy that you might have, and laying out what that strategy is. And then if you do have the ability to go into automation, that is another way to further enhance reliability, which also will come into resiliency, which I'll talk about in just a second. And then some of those are, for example, we have a solution we call laser, which can allow fault location and isolation and restoration very fast. So you can isolate exactly where the fault's at, get the lights back on very quickly. And when you talk about reliability, it's about how much you can keep uptime for those customers. And then in some cases, as the grid is changing, you might want to install other types of equipment to supplement when you have, for example, fault current levels switching and beyond where certain equipment you might have put out can handle. And that's where we have the clip product that Kyle had mentioned that can enhance fault current levels. Now, the next thing is resiliency. Resiliency is starting to become a bigger and bigger issue. Resiliency is when you have these low frequency events, but really, really high impact. In North America, in Australia, and some other areas, we're suffering from wildfires, which are triggered by some of the climate changes that we're going through on the earth. You also have many typhoons, floods. It seems like these very impactful events are happening more frequently. And the things you can do to improve resiliency of your grid, and this is very critical, you should look at how can I improve resiliency and reliability using some of the same equipment strategies. And this is a key point to maximizing the cost benefit that you can obtain. So some of the things that Kyle shared about grid hardening are part and parcel to solving the resiliency challenge, such as dealing with wildfires by putting out equipment that doesn't maybe have as much oil, where you have solid dielectric type of equipment, or you don't have open areas that can spark. You have fully contained equipment where you can have different types of technology to do so high impedance fault detection, for example, so you can find out if there's an issue with a down conductor, be able to deal with those things. And then also you need to look at things like cyber attacks and how do you deal with those. So these are like non-technical threat vectors that might be interesting to look at. So we encourage a holistic view: equipment, automation, and also consider your cyber strategy. And then if you look at some of the strategies that are similar to reliability, adding more switching, protection, and automation. Automation in particular to help reroute big blocks of power if you have a section go out that is severely impacted. And you might have critical infrastructure locations, and they're microgrids, as earlier was mentioned by John. Microgrids is growing for critical installations. Those might be like hospitals or other really critical areas that you just cannot afford to lose power. Putting out more sensing, more ability to see what's happening, helps you deal with resiliency challenges more. Undergrounding. And another thing is looking at your poles and how you put your overhead poles up to make sure they are very strong and can hold up under wind load, rain, etc. So we're very active in deploying these type of solutions across the globe, and those in terms of automation, different types of equipment, etc., including microgrids. If you look at the cost, and I was going to just share on here about the cost and how you might improve cost, because I think you mentioned about that as well. It is challenging when you talk about the amount of equipment that is needed to be deployed in order to deal with these reliability and resiliency challenges. So some of the strategies that we've seen successfully employed is to look, when you're planning deployments of technology, to look at the total cost of ownership model, not just the upfront cost, and to consider it over a period of time, because the equipment to be deployed, including the expense of putting this in and the resource challenge of putting this in, can be very daunting. And so really look seriously at the total cost of ownership over the life cycle and plan to get equipment that is hardened up front. It's better to spend a little bit now and have equipment that can handle these challenges. So you're putting equipment in for reliability, but at the same time, you're enhancing your resiliency against things like weather extremes from typhoons, wildfire, and so forth and so on. And look at the exact application and environment. We see many cases where large amounts of a specific technology is deployed, but they didn't look and say what other supplemental types of flexible architectures might be needed to create a holistic distribution strategy. And this is where we've worked very closely with our customers around the world to help them design a very solid distribution deployment strategy so you can get highly resilient equipment and be able to build reliability reliably. And some of the things you can look at, for example, is you may not be able to have full deployment of automation on the front end, but we can help you design a strategy so that over time you can then automate with perhaps more automation, or maybe you can do field automation and then later get model-based through software, et cetera. And having that deployment strategy over time will help you improve both reliability and it'll help you improve your resiliency. And you can mix underground or pad mount type technology with overhead technology and supplemental technology like additional fault current protection in isolated cases to help you build the most capability with the least investment necessary to get the big bang for the buck.
Mm-hmm. Thanks, Ron, and Kyle earlier for your answers there. I think there's a lot that's resonating with our audience. We have had a question come in. Just a reminder to the audience that we are taking questions. Please do feel free to send in your questions at any point as they come to you, and we will we'll do our best to work our way through these. Carl, just picking up on your final point there around and cost and kind of working with your customers to ease that burden. We've had a question here that's relating specifically more to the smart grid system. I assume that means the sort of digitalization piece. You touched on solutions there around grid owners that you've worked with. This question is specific to a small utility with a customer base between 150 to 300,000. Is there anything specific that you would lean on for that? Is there any insights that you'd share on utilities, suggestions for utilities with this size for implementing smart grid solutions?
Yeah, absolutely. That's a great question. And we do recognize that a full, complete smart grid scenario for your entire grid may not be feasible for every size utility, large or small. So some of the approaches that we've seen that have been prudent with some of our utility partners is, I think Ron mentioned this, kind of taking a step back, holistically looking at your system and determining what some of your greatest areas of weakness are, what some of your greatest areas of challenge are. Those could be problem circuits. Those could be, critical customers with, airports, critical manufacturing processes, areas where it's unacceptable to lose power at all. And once you kind of prioritize some of those things, start looking at automation as a tool, maybe in those areas. And again, depending on what your problem is, can help drive you towards what part of that intelligence portfolio would be a good fit, right? So John mentioned challenges in power quality. If you're struggling with power quality issues, maybe the deployment of sensors or solution to gather more higher accuracy measurements on your grid on what's happening could be valuable. If it's losing customers or reliability challenges, implementing devices like reclosers or maybe a small scheme of reclosers to do a small scale automation scheme like Flizzr could add a lot of value in the right situation, or it could simply be selecting a few critical customers and finding a way to route additional alternative sources of power and tying that in with some automation to do source transfer. So those are a couple of applications that I've seen utilities that weren't ready to do full bore whole system SCADA driven automation, but they were able to find value using those technologies in applications that made a difference for some of their critical situations.
Kyle, we've had another question come in here that I'm going to point your way. The question is, what's the cost ratio already considered in pad-mounted transformers, switch gears, and distribution panels between underground distribution system and overhead? It has been proven that UDS is highly reliable and resilient, yet what holds us back is the cost of implementation. Do we see market price reduction for this technology in the future?
Yeah, that's a great question. Obviously, price sensitivity is very important. Some things I want to highlight on this, Ron mentioned this as well, but I want to reemphasize it. Some of the newest, latest, greatest technologies being developed, it's really important that they're evaluated on a total life cycle perspective. G&W included, a lot of manufacturers are building a lot of resilience, durability, capability into this equipment. And if you're comparing that with legacy technologies that weren't designed to last as long, that don't have that type of resilience built into them, that you're going to have to change out more often, if you're just comparing the upfront price of the asset, it can be difficult to justify the two. But we've done a couple of exercises where we've met with utility partners and we've talked through maintenance costs, change out costs, if there aren't the ability to reset or automate the equipment, it's using more primitive protection devices like fuses, factoring in holding that inventory, time to roll trucks to replace that. We found that from a total life cycle perspective, some of this newer maintenance-free technology is actually more cost-effective than you might think. So I think that's an important part of the evaluation. But with that said, I think the message has been received, and I know G&W is always looking for ways to develop the technology to fit the market with the right feature set and the right cost point. So we always welcome feedback on areas where the value of the product provided, there's a gap in what you feel the value is from a utility perspective. So we welcome feedback on that.
Thanks for the questions. Please do keep them coming in. My next question, I feel that we've touched on a bit of this, but there was something that mentioned in John's presentation that I'd like to tie into this question. You've touched on some of the solutions to help future-proof a system. Perhaps you can outline some more of those, but also John mentioned in his presentation SF6. Now that's something that we've come across more and more in the region. Traditionally, regulations here in Southeast Asia do lag behind, but I know that some of the utilities in the region are taking their own steps to look at SF6 free technology and are future planning in that way. Perhaps you could outline some of those future-proofing solutions that you have and just touch on SF6 in that response.
Okay, I'll be happy to touch base on that. So in terms of future-proofing, this is a really important aspect that must be considered when looking at deploying distribution or even transmission equipment, because the product you're putting out there is going to need to last in these really robust environments, the increasingly robust environment that we're living in now for quite a long time. So some of the things that are really important to consider, and one in particular that's sometimes not paid as much attention to up front as it should be, is what are the maintenance requirements for the equipment over time. So one of the things we focused very heavily on, for example, and one of the reasons we've had the success we have in many regions of the attendees here, is that we focus on trying to build equipment that has the minimal maintenance requirements possible over time. For example, if you buy equipment that is solid dielectric, you don't have some of the challenges with maintenance, et cetera. Another thing is looking at the equipment and saying, okay, maybe I don't have an automation strategy today, but I know that's the future, and that's where the future is headed. More and more information, more automation. So planning that up front, finding a vendor or equipment that you can buy that has flexibility to deploy different types of automation, and that you can fit the automation to your specific needs. And even if you can't put in place, for example, a software-based, model-based system that can communicate to field devices, go ahead and equip the field devices so that can be a future upgrade at minimal effort and minimal additional cost. Another thing that is really critical on future-proofing is not to think of it just as an individual piece of equipment, but look at your distribution grid as a whole and find what information do I need to be gathering from that distribution system to help me make the equipment choices of the future. And those are, for example, putting more current and more voltage monitoring out to be able to understand what's happening in the grid so that you can start to get visibility of what to do. Now, that will require some collection of data, and you have to figure out how to manage that, but that'll help you plan for these future strategies that you're going to need to promote. So that implementing control flexibility, making your equipment so that it can be upgraded in the future to be able to deploy new strategies for distribution, and buying equipment that's low maintenance and field robust to be able to last long term. These are some of the key strategies for future proofing. Now, if you look at some of the trends, as mentioned about SF6, we know that a trend that's going on globally is trying to control the release of greenhouse gases. And of course, SF6 is a very potent greenhouse gas. And if it does leak out of equipment or get out into the atmosphere, it is very damaging to the atmosphere. So this is a very important consideration. What we've been doing in G&W is we've been working very hard to make more and more equipment that is solid dielectric or that uses air or air mixtures that does, or other gases that do not use greenhouse gas effects. So we have that ongoing in our underground equipment. We have underground equipment that is not requiring SF6. We have solid dielectric overhead equipment. We have some equipment that has even historically been SF6 that we've been able to migrate away from SF6, such as one of our overhead products sold in Asia Pacific area, the ORA. We also have Trident solid dielectric switchgear that does not, which is pad mount, does not have any SF6. Our recloser technology, even up to 72 kV. So we even have 72 kV recloser that can also be a switch or can replace a circuit breaker, and no maintenance and no SF6 required. So it is key to look at what technologies are out there. And of course, there's a big focus across the globe, across all vendors, to find ways to mitigate and to get away from SF6. So it is a very important consideration, and it's something that more and more equipment is becoming available as the days go on.
Thanks, Ron. Kyle, how can utilities protect service areas during and after severe weather? It's something that's been mentioned a lot in the last 45 minutes, this increasing extreme weather. How do utilities protect service areas?
Yeah, absolutely. I think we've talked about a lot of the core building blocks there. I mentioned the importance of specifying and using equipment that's hardened for these type of conditions. That's kind of foundational. Having that equipment be able to remain energized or even operated during or after restoration efforts are going to keep your personnel who are stretched in those type of events focused in on addressing the real problems and getting the system restored as quickly as possible. So submersibility of the equipment, I think, is really a big one. But one of the areas that's gaining a lot of traction in North America, I'm sure you guys have seen it on the news and it's been mentioned on this webinar, but is wildfire protection. Very, very hot topic right now in North America. And a couple things I want to mention that can help some strategies to mitigate wildfire reduction. I know Ron made some mention of technologies from a control and protection standpoint to identify scenarios where you're doing high impedance fault detection or technologies that can identify a falling overhead line. But a couple other things that I thought would be worth mentioning to this audience is the importance of specifying and utilizing equipment that has a dead front design. Dead front design meaning that when energized and the system's connected, there are no energized components on the exterior of that equipment. In underground applications, that's very common. If you connect a submersible separable elbow connector to a piece of dead front equipment, everything's at ground potential, which really eliminates any risk of wildlife or some environmental condition creating a fault, which could create a spark, which could be an ignition source. One of the things I want to highlight about some of our overhead products that Ron mentioned are Viper reclosers, our ORA sectionalizing switches used in the territory. We utilize a dead tank design. So while there still may be live connection points to connect to those overhead lines, a significant portion of the rest of that design is at ground potential, again, minimizing the opportunities for something to happen that could create an ignition event. And last but not least, the clip product that John mentioned, that really cool system protection device. If you're not familiar with that device, it has the capability to interrupt faults much more quickly than a traditional circuit breaker. It can clear a fault in a half a cycle or less, in parallel with reducing the amount of let-through energy. So those two things together can do wonderful things for reducing stress on the system, preventing things like arc flash and blast downstream, again, which are common sources of ignition from a wildfire perspective. We even have some customers who are making sacrifices from reliability to resiliency when there's high winds or conditions where fire conditions are ripe. They're changing protection settings or enabling devices like clips or putting reclosers in different protection schemes such that they can turn the power off much more quickly, or even preventatively to, a short outage may be a better end result than something igniting it or starting a wildfire. So those are a couple more things that we didn't talk about that I think can make a big impact to some of the trending severe weather events that we're seeing around the world.
We've had a comment here on SF6 that I'm just going to field myself here, just based off the conversations I've had with others. From a user perspective, SF6 impact is minimal. Yes, that's probably true. However, the regulatory frameworks around the world are increasingly cracking down on this sort of thing, certainly in Europe, and the expectation is that the region will follow suit. So yes, I agree that low impact versus high cost make it hard to justify, but at the same time, it may be something you may not have a choice in the future, and hence the question around future proofing. The question I have next is something that is relevant, particularly given where Enlit Asia is going to be held in November. I need to sneak a little comment about the event coming up in November, obviously, in Indonesia around microgrids. My question is, it's something that's been mentioned a few times. You're obviously very proud of your microgrid, and we do have a pre-recorded discussion around that microgrid, which the audience can see on our website. How can utilities connect to the renewable energy sources or microgrids?
Okay, I'll take a stab at that question. So one thing that I'll point out is about microgrids in general is that they are sort of the ultimate resiliency play. And so microgrids you typically would have, and I'll start with microgrid discussion. You typically have, when you have microgrids, a lot of different interoperating parts. And so one thing that's a challenge with microgrids is making sure you have all of the right pieces and parts connecting it. For example, you need to consider the grounding transformer that you have there and how you would switch that on and timing the switching of that. You need to look at the type of switching devices that you'll have disconnecting from the utility, because you have the utility. And you need to look at how you're going to have the overall strategy for how that microgrid is going to work in terms of how you're going to justify the investment. There's many ways to utilize your microgrid, for example, to potentially even sell power back to the grid in some cases, or to provide more grid stability in localized regions, so there can be benefits back to the grid. So looking at the entire business case and then looking at the different pieces of the technology, if you're using a microgrid for industrial facility, a critical industrial facility, for example, you may need to deploy a flywheel to keep equipment running smoothly with no interruptions when you have the switchover, et cetera. And so microgrids are a little bit complicated to implement, but it is a very unique way to bring huge reliability. And that's an area where we've deployed all these different technologies that can offer those. Now, if you talk about connecting into renewables, and microgrids and renewables often go together. The microgrid that we have, for example, in our facility, we use solar panels, and then we have that connected to the microgrid. Renewables have some challenges associated with them, particularly if they're inverter-based renewables, which is what you would have with solar or wind. As John had mentioned earlier, these increase the likelihood or possibility of harmonics, and you can have a lot of different types of frequency swings in very, very quick fashion and transients. And these harmonics and transients can cause damage to equipment, premature aging of equipment, and other types of issues. So you need sensing at your microgrid or at your renewable interconnections. You need sensing that has bandwidth. So not typically a traditional instrument transformer, but you need some sort of voltage sensors and perhaps current sensors. And then you need a way to monitor those power quality signals using high frequency, or rather high sampling rate measurement equipment that you can measure what's happening there. And then as you start to have these renewables employed, you also have to look at the type of fault currents they can create. Renewables like solar cannot create the same level of fault currents as spinning generation, but it can change the fault current characteristics in the local vicinity. So you also need to be very careful to monitor in the local vicinity of where you interconnect and intertie to these renewables, what's actually happening at that location. And that's an area we've been specializing in for quite some time with reclosers, AccuSense sensing technologies, and so forth.
We have time for one last question. If I can direct it to you, Ron, and ask that you keep the response to a minute or so.
Yep.
The question is, I've just managed to lose it. What are the effects to consider that could affect the distribution system when implementing undergrounding programs, for example, ferroresonance?
Okay, so I'll mention three things that that I've seen come up, and I've been in this industry for 30 years, so I've seen a lot of these type of questions come up. Three things that come up that I've seen people run into when going from overhead to underground, which is happening more and more as we try to make the grid more resilient. One is you have to keep in mind the sizing of the cables. Overhead cables are bare for a reason. They can dissipate heat. Underground cables do not dissipate heat as much, and you have to make sure you have proper sizing. Otherwise, you get premature aging and you can have faults underground. Faults underground are much more difficult to manage. Speaking of faults underground, another key point is cable joints. When you create cable joints, that is an opportunity for an issue. This is an area with our cable accessories group we've been specializing in for decades, and you have to have very reliable joints when you go underground, and when you transition from underground to overhead, you need to look at the joints as well. And you also look at how do we do that in a way that's most efficient. That's an area we also focus on. Ferroresonance, that does happen because of the changing capacitance of your distribution system. So there are ways to mitigate ferroresonance. You have to look at your substation design nearby when you go underground. Try to avoid, when you have delta transformers connecting to Y, you can have issues like that. So look very carefully at your distribution planning. And then if you have ferroresonance possibilities in an area, and areas like in Europe where there's a lot of underground technology, mitigation technology does exist to mitigate against, for example, potential transformers going into a ferroresonance situation. We understand those technologies and can deploy those technologies as well. So there are technologies to deal with these situations, and that's an area we specialize in helping our customers with. So, but those are three things to look at. Mitigation technology for PTs, ferroresonance, how you connect your power transformers transitioning from delta to Y on underground, cable joints, and heating of cable.
Thank you. That was spot on, about a minute or so. John, if I can ask you to come back. Ladies and gentlemen, we have reached the end of the panel. We don't have any more time for questions. Thank you very much for those that did send them in. If you have any other questions, the contact details for the speakers today were on the presentation, and they will be shared with you. So if you have any follow-up, then please don't hesitate to reach out to G&W. John, can I ask you to share a few key takeaways?
Yeah, so we prepared a short slide here just to highlight some of the things that we thought were important from our discussion with you. I appreciate this opportunity to share our knowledge with the audience. But these 4 key takeaways we feel are important. So it's important to consider hardening the grid as a way to improve reliability and resiliency. And both Kyle and Ron talked about a number of technologies that enable that. Things like undergrounding, things like choosing type devices, which minimize the impact of the environment around it. Choose manufacturers that produce very robust equipment that will allow it to survive not only changing grid environment, but also difficult environmental conditions. The next point we wanted to highlight was to try and consider the total cost of ownership when you're evaluating particularly a new piece of technology. These are devices that should be expected to operate for decades. Going beyond just the initial cost of the equipment, consider what it's going to take to install, how flexible it is in terms of installation, how inexpensive is it to operate, what are its maintenance requirements. Even consider what its disposal costs might be. All of these are very important when considering the overall cost of the product over its life. The next point is to consider products and technologies that will allow you, that will grow with your changing needs. One of the things that we keep hearing from utilities is that they know that the grid's going to change, and no one really knows what exactly that specific impact is going to be on them. And so you need to keep your options open, you need to be flexible, and you need to be choosing technologies that allow you to change with time. And some of those technologies might be considering adding sensors up front, or you may choose technologies that may allow you to do that in the future. Some other things that you might consider are your controls, your IEDs. making sure that you choose control platforms that allow a multitude of different communication protocols, so you're not locked into something that's proprietary. Choosing manufacturers that are very agnostic with the components and the partners that they choose, give utilities flexibility for the future so that they can choose their path as they go along. And then the final key takeaway that we thought was important is be very strategic in your consideration of how you add intelligent devices and automation to your system. There was a question about this earlier, that you cannot go big initially. It's very costly, it's very risky. Try and find small pilot projects that allow you to demonstrate the technology, demonstrate the benefit of adding these advanced technologies to your grid, build experience and knowledge as you go, and that will give you more confidence and a clear vision of how you can proceed forward. So as Simon mentioned, we really enjoyed having this discussion with all of you, and if you'd like to consider continuing the conversation, here's our contact information here. You can speak to Ron, myself, or Kyle. All three of us will be at the Enlit Asia show in the middle of November in Jakarta. So come visit our booth, and we'll be happy to take all your questions then as well.
Thank you very much, John. That just leaves me to wrap up finally. Thank you very much to the audience for being with us this morning and for engaging and asking questions. Thanks very much to the speakers, John, Kyle, and Ron. Thank you very much for taking the time out of your evening, as it is for you. Thanks also to the sort of wider G&W Electric for hosting this discussion. I know that there's a lot there that will resonate with our audience today. Lastly, I encourage the audience to attend Enlit Asia in Jakarta, 14th to the 16th of November. G&W will be there. You can meet with the gentleman who shared insights with us today and discover more about how G&W can support your operations now and in the future. Last point is attendees. You will be, I think, shared a brief survey post event today. Please do take the time to answer that. Your feedback is very helpful in ensuring that we are providing you with valuable and quality content. From G&W and from the Enlit Asia team, hope to see you in November, and thank you very much for your time.